So next speaker is Farooq Khan. Farooq got his bachelor's and PhD degrees in France, and then joined Bell Labs and Ericsson, and is now at Samsung, where he's president of R&D America. And he's in charge of a bunch of things, including wireless communications, antennas, sensor and IC design, multimedia communications, and so on. He has authored over 40 research papers and has over 100 patents. He also wrote the book on 4G mobile broadband communication, and I can see that he's already working on the next book, which is going to be called 5G, and that's what he's going to talk about.
Thank you, Alon. It's my pleasure to be back here after 3 years. I was here 3 years ago, and at that point, I gave a talk on millimeter wave mobile communications. At that point, we did not call it 5G because 4G was taking its baby steps. But now, as Gabriel said earlier, 4G LTE is not meeting the user experience, and we need 5G, so I can call that technology 5G now. Actually, mobile communications, along with the internet, has been the most transformative technology in the history of humankind. This technology had touched more lives than any other technology. Actually, we can say that 50% of the Homo sapiens who ever walked on this planet are using this technology, because 50% of the people who ever walked on this planet are alive today due to population growth. And this transformation has been more profound in the developing countries than in the developed world. In the developed world, it was more like cutting the cord. I had my landline phone, now I can have my mobile phone. I can, for example, do my banking by going to a physical bank or maybe on a desktop, and now I can do it from my mobile phone. Similarly, I had a hospital, I go there, I can get my information on desktop, now I can get health information on the mobile phone. Same with education. So this was an incremental, in my view, transformation in the developed world. Even from socio-political point of view, for example, in the 2008 elections, one presidential candidate used smartphone and technology more than the other candidate, and the candidate who used this technology won the election. But from the common person point of view, the impact was not that profound. But for example, with the Arab Spring and so on, we saw that with this technology, people can get rid of decades-old dictatorship. So what is, Gabriel earlier said 4G cannot meet the demands. What is the issue? There is a big increase in the mobile connections, and then in the mobile data traffic due to these new applications, video streaming and social networks and so on. And you can just see, like in 5 years, 10 times projected increase in the data traffic, and more application in the cloud. So you will have gigabytes of data flowing back and forth between the cloud and your mobile devices. And also Internet of Things. Today we have maybe 7 billion connections, but it is expected to grow to more than 50 billions in the next maybe 6 to 7 years. So this is how I see it. Personally, I have been involved in kind of designing the next generation of mobile communications, starting from the first generation AMPS cellular communication. So I always felt very proud and proud of my work because we always had capacity more than the demand. So this is what I call communications engineer pride era until 2008. So we were always ahead of the demand, and as a researcher, it feels so good. Okay, I designed something, now even I'm leading ahead of the market demands and so on, because I had great ideas. I always provided the capacity that is needed. And but this occurred to me in 2008 when we completed the 4G LTE standard, and I was just wrapping up writing my 4G LTE book, that this realization that this time, even the system, even before we designed this system, it's not going to meet the expected demand. And this is, many of you are aware of the 2008 financial crisis, but I call it wireless communications engineer crisis. That recession and depression is over, but we are, personally myself as a communication engineer, going through that depression because, recently I had a personal experience. I have a data plan and you are expected to get a $60 bill every month. Suddenly I got more than $600 bill. And apparently operator put in some caps and so on, and you go a little bit over that and they charge you so much. I tried to settle the matter with my operator. They said, we communicated you this in a fine print or something. And then I decided I should file a complaint with the Better Business Bureau. If you go to their website, there are top two things. The first, they say, selection is if you have a complaint with a car dealer. And the second one is if you have a complaint with the mobile operator, and then everything else. I felt really shameful. I said, this is my fault. As a wireless communication engineer, we did not design technology that can provide the capacity. That's why operators now need to put on these caps, and that's what resulting in this situation. And what was the reason? In 2008, suddenly, so one data point we can see is the debut of Pope Benedict versus Pope Francis in 2013. You can see the devices here. I could not spot a person who did not have a smartphone or a tablet. And here it's very difficult to find. Actually, there is one flip phone. My daughter told me, yeah, there is, when I showed her this picture. So the things completely changed. We did not have any idea about this growth. So now we cannot do little. We were used comfortable here doing incremental innovation, but now we cannot do incremental innovation. So we need to think big. It's no longer good enough to have 2 times more capacity or even 10 times. We need to provide thousands, 10,000 times more capacity to meet the expected demands in the next 10, 15, and 20 years. And how we can do this, what I call it wireless data omnification, basically. Omnify, I call it, stands for orders of magnitude increase every 5 years. This means we need to increase data capacity by 10 times in 5 years, 100 times in 10 years, 1,000 times in 15 years, 10,000 in 20 years. So this is not possible. This is not impossible. Actually, the other technologies like storage and computing, riding on the Moore's law, experience this type of growth. In the last 30 years, computing power experienced 1 million times increase, and similarly storage. So only wireless communication is lacking behind, but we need to do this too. So there is already computing and storage capabilities available. The limitation right now is really the connectivity and communications. And you can see, it's, if we started with 1 megabits per second in 2000 with 3G, we need to go all the way to 1 terabits per second with 6G in 2030. In 30 years, 1 million times increase in peak data rates, and also in capacity. And the life, we are not even halfway, maybe in 2014 or somewhere. If you have an exponential growth like this, the life becomes much more difficult in the later parts. So the life is not easy here, but we need to do that so that we can provide mobile communications at affordable price, not only in the developed countries, but also in developing countries where, we pay $60 for the data plan here. A big fraction of the world, their monthly income is less than $60. So in order to provide the financial, education, health services to the developing world, we need to have this type of orders of magnitude increase in capacity and also bring down the cost per bit. So just some history of mobile communications. The first generation systems deployed in the 1980s were used for voice communication. And then the major shift happened with digital communications. The big thing here was the transformation with digital signal processing. You have a voice codec to compress the voice signal, channel equalization to cover the ISI due to multipaths, and also channel coding. And with the digital nature of this communication, so every new generation actually does three things. It increases spectral efficiency in bits per second per hertz. It provides uses larger bandwidths to provide higher data rates and enable new services. So first G was more about voice, but due to digital nature of 2G, SMS service was introduced, text messaging. And then the big transformation, of course, in 1993, turbo codes were invented. Late 90s, LDPC codes were reinvented, and also 1998, MIMO was invented. So these technologies, further based on digital signal processing, made into 3G systems, which used even larger bandwidth, like 5 megahertz, enabling like video communication and other applications. And another thing, then we almost reached the link capacity limit. With turbo codes, I could operate within a dB of the Shannon capacity limit. And then many people said, oh, nothing more needs to be done there. But with MIMO, we discovered that that limit is only for one transmit and receive antenna. If we have more transmit and receive antennas, then we can get higher capacities. So that was the case with 4G, where OFDM technology and MIMO were introduced. And then the limit is not fixed. You can have more antennas, you can have higher and higher capacity limit. But the problem is all mobile communication, for that matter, all radio communication, including your TV, AM, FM radio, and others, always used a spectrum up to 3 gigahertz. And that spectrum is now heavily crowded. And I cannot increase, I'm already operating at the Shannon capacity limit. So I cannot improve the link capacity. Gabriel earlier showed the Galaxy S5 and maybe a given number of antennas. I cannot have more and more antennas. I need antennas for different bands. And then the whole, in the size, I cannot have like 16, 64 antennas. So I cannot kind of continue to do MIMO and increase capacity. And all the bandwidth is crowded and limited. So what we need to do with our 5G and 6G vision is go in higher frequencies, millimeter waves, like 10 times higher frequencies. Then you have 10 times larger bandwidths. And the good thing is now your antennas are 100 times smaller if you consider 2D 1010. So now you can have a lot more antennas. You have order of magnitude more spectrum. You can have 2 orders of magnitude more antennas. So this is how you can have maybe orders of magnitudes increase in capacity with millimeter waves. But the life is not easy there. Channel characteristics are completely different. RF and device component efficiencies are low. So there are big challenge in order to enable mobile communications in millimeter waves. So many people ask me why you chose to do millimeter wave frequencies. I have one political answer that's based on what John F. Kennedy said during the space era. We chose to go to the moon not because it's easy, but because it is hard. At that, US is the most technologically advanced country. If we are not going to the moon, nobody else is going to go there. So as the largest technology company in the world, Samsung and mobile communication as our largest business, if we are not going to take this risk and do this, no one else is going to do that. And my other answer is more technical, and people say it's a very high frequency, 10 times higher frequency. I asked them, what is the highest frequency you can get? What is the limit on frequency? Based on, is there a limit on the maximum frequency you can get? But then to show them, I came up with this, what I call the, I'm calling it the Planck frequency because it's calculated based on the same three fundamental constants of nature: speed of light, Planck's constant, and the gravitational constant. That's the only thing I can believe as a limit. And that limit is, you can see there are already 9 zeros in gigahertz. So that's 18.55 billion trillion gigahertz. Of course, I cannot achieve this frequency because at this frequency, this photon is going to have so much energy because your energy is proportional, Planck's constant times frequency. So this will create a kind of miniature black hole. But anything below this is possible. So when they tell me, oh, you're talking about 28 gigahertz, very high frequency, I just tell them it's a billion, trillion times smaller frequency that compared to the limit that nature has provided us. Then they say, okay, you go higher in frequencies, my devices cannot operate at that frequencies. Devices need to become smaller and smaller because to have the FT and higher and higher for the devices. Then my colleagues in the semiconductor business tell me that we have now reached the limits with 20 nanometer or whatever. We are now talking about only a few atoms in the channel and so on. I said, who said we need this charge flowing in the devices to make transistors? Then they asked me, what do you think? how small these things can become? Then again, then I just show them the Planck length, which is, I say, yeah, you can, Planck's length is the only lower limit in size I know about. And then they ask me how small it is. When I tell them it's maybe 10 to power 34 smaller, it's very hard for humans to comprehend these numbers. So I tell them, if you blow up your transistor to the current transistor, 20 nanometer, to the size of the universe, which is observable universe, 93 billion light years, then Planck's length is your 20 nanometer transistor in that universe. So this is, again, it's very difficult for humans to comprehend that type of big numbers. So my point here is, we have not been aggressive enough. Maybe we have put in some artificial constraints, and we need to maybe think big in order to overcome, so that we can overcome this digital divide and provide this unlimited mobile connectivity and communications to every human being on this planet in an affordable way. Then user experience, again, I think, we focused on more increasing the peak data rates until 4G, because what you could do is, if you're closer to the base station, I can use like BPSK modulation than QPSK, 16 QAM, 64 QAM. So you can get very high data rates closer to the base station, but if you are at the cell edge, your data rates are very low. It's because I move away from my base station, signal goes down, and also the interference goes up. So one of the things with millimeter waves is I can have now narrow beams. I mean, I can have high gains due to large number of antennas. So I can boost the signal strength. And since the beams are narrow, they are less likely to collide with the beams from the neighboring cells. It's no longer a broadcast channel. It's more a dedicated beams. So that will improve your cell edge data rates as well. And then, of course, reducing. So our goal with 5G is not only have like 10, 100 gigabits per second peak data rates, but also having a more uniform user experience. I mean, this is, again, something to look at, and collected many things here, but I think earlier Gabriel also mentioned about the user experience, but this is what we have been optimizing, bits per second per hertz. I mean, so we had sophisticated digital signal processing techniques, BMO, MIMO, beamforming, channel coding, and then we reached the limits on this. But now we say we can get more hertz. I mean, nature has provided us with unlimited bandwidth and frequencies. And similarly, I mean, when I was calling it a 5G metric, I mean, then I looked at the faculty profile of Center for Wireless Communications. I mean, I said this very well can be a performance metric for this center. I mean, you are pretty much working on every aspect of that. I mean, data compression, because I want to reduce the number of bits video is the biggest traffic, and also with cloud applications, things sitting in the cloud, I want to minimize the amount of data I'm going to retrieve from the cloud. And also more, this is the thing I mentioned, I mean, having higher data rates in a geographical area, even at the cell edge. I can do that with beamforming and small cells. And now I'm saying we can get hundreds and thousands times higher data rates. And the thing is, battery technology is not evolving. I want to have those data rates in these handsets. So my power available budget is the same. That means my power efficiencies need to go up by orders of magnitudes. So this is what these low power RF devices systems and algorithms come in. And also channel coding. I want to decode my code word with the least energy possible, with least number of cycles, and also with the least cost. So this is, so we want to maximize the user experience while developing all these technologies, and also do this at the lowest cost possible, so that this, the very, very high data rates become available to all the people on this planet, so that they can benefit from these technologies. So I'm going to show you some of the field test results in the millimeter wave that Samsung has been doing. So we developed a system at 28 gigahertz with 500 megahertz bandwidth, 64 antennas. With 64 antennas, your beam width is just 10 degrees wide. And of course, thanks to Professor Urbanke, we are using LDPC codes because they give you capacity with minimum complexity. So this is our base station system and mobile station. So we did a line of sight testing up to 1.7 kilometers, but we still had more than 10 dB power headroom available. We can actually go up to 4 kilometers distance. These are the base stations with the same power levels as the existing 4G base station. So there's no issue with the range in line of sight. We also did non-line of sight testing. These are our campus in Suwon. Maybe Gabriel earlier mentioned one of our antenna buildings. That's one of these buildings. And we can easily get up to hundreds of meters non-line of sight. Many people have this kind of misconception that, millimeter waves, you cannot do non-line of sight, but later I will also show you some simulations. The energy is not absorbed when millimeter wave hits some obstacle. It's actually reflected, so we can kind of leverage those reflections to still provide non-line of sight coverage. And then we also did outdoor to indoor penetration. Again, we can cover maybe a couple of 100 meters distance, and also a non-line of sight with mobility up to 8 kilometers per hour. You can see the base station and mobile station moving at 8 kilometers per hour. And also multi-user, because we want to have multiple beams, from the same base station going to multiple users. And then this is one of the urban environment. I think it's maybe 928 meters by 586 meters. We covered with 10 base stations at 28 gigahertz frequency, 1 gigahertz bandwidth. I will show you some simulations in this type of. So I have a video. I'm going to maybe.
Recently, millimeter wave technologies have drawn keen interest as a method to support explosively expanding wireless data traffic. Here, we are going to envision mobile communications using millimeter wave beamforming in the dense urban city. We modeled real building structures and architectures in Ottawa City, Canada, and deployed multi-base stations in millimeter wave bands for ray tracing simulations. For the given area in the simulation, 16 base stations with 200-meter intersite distance can provide the overall satisfactory received signal quality, and 10 base stations are good enough through the optimization of cell planning. The propagation characters of millimeter wave are analyzed to fit very well in small cell deployment. Beamforming is the key enabling technology. Once mobile station performs the initial network entry based on beam searching algorithm, then the beam tracking algorithm keeps the stable connection, even in the multipath environments. When mobile station is crossing the cell boundary, multi-BS beam tracking algorithm is performed for smooth handover procedure. Sometimes the connection environments can rapidly change. In this case, multi-BS connections can be helpful to maintain the seamless services. Throughout the simulation, the user data rate was analyzed to be at least 4 gigabits per second with 1 gigahertz bandwidth, and wideband processing technologies and various beamforming algorithms would be key players to make it real.
So you can see, these are simulations assuming real buildings and the reflections and everything. So people have been thinking like millimeter waves from point-to-point communication. Yes, if I have a transmitter here and receiver here, it is blocked by a tree or a building, the signal will not get through. But the cellular systems are completely different. I have many base stations. I cannot get to this base station, but I can get to the base stations over there. And also, the signal is not absorbed and lost, it's reflected. So the communication is at lower bands, it's more due to diffractions, signals can bend around the building corners and so on. At millimeter waves, communication is going to be more based on reflections. And also, you have multiple base stations. So when we look millimeter waves from a cellular deployment point of view, where you have multiple base stations, and also you take into the reflections, you can see, we can get multi-gigabits per second data rates with 1 gigahertz bandwidth. So this is a very important key point that we need to understand. It's a communications happens in completely different way at millimeter waves, as you have seen from these simulations. So there are a lot of initiatives around the world now in Asia, Europe, and the US around 5G activities. Since we are maybe running out of time, I will maybe just show you. I mean, as you have seen, a new generation of mobile communications happens every 10 years. 1G in 1980, 2G 1990, 3G 2000, 4G 2010, and we can expect 5G is going to happen in 2020. But all the four previous generations were where we were in the wireless communication engineer pride era. So, but now we are in, I mean, what I call it a disgrace era, because we are not able to meet the demand that is out there. So, I mean, we need to do 5G, these larger capacities even maybe earlier than 2020. And from Samsung point of view, we are planning to do some pre-commercial trials in 2018 in Korea. There's a Winter Olympics in Korea and many other countries, I think Japan for 2020 Olympics and so on. So the question I had, will we have 5G by 2020? The answer is not yes or no, but I mean, in my view, we must have 5G by 2020 in order to meet these growing demands, so that we can be, I mean, not only in the developing countries, but most of this now new growth is going to come from the developing countries. I mean, changing their lives from education, healthcare, financial services, and even agriculture point of view. Okay, and I think maybe a summary slide. So again, I said we want to maximize the user benefit by reduction in the cost per bit. I mean, one way is having a lot more spectrum going at higher frequencies, then the cost of the spectrum is low. That means now I can get very high data rates at a very, very low cost. And in our view, we have been doing research on millimeter wave technology for the last 4 years. Our confidence now has gone up over the years, and we really think, this is a feasible technology for mobile communications. And I did not cover the RF front end. As Gabriel said, even some 4G antennas are only 20% efficient. Now I want to have orders of magnitude reduction in the power per bit. So, I cannot live with the lossy devices or circuits or systems. We need to have big improvements in device efficiencies, antennas, systems, and develop algorithms that can provide these high data rates at a very low energy cost and also at a very low dollar cost to, again, making this technology available to every person on this planet, the gigabits per second user experience. Thank you. There are various ways of looking at it. Indoor, the Wi-Fi is also available, right? So, and also, whenever we have a new generation of mobile, the previous generations stick around for many years and many decades in some cases. So with the initial deployments of 5G, we can see where in some cases you will need to fall back to 4G or Wi-Fi if you cannot penetrate through certain buildings. But our results have shown that particularly in the US, where we have a lot of glass and sheetrock. I mean, it's not any significant more loss at millimeter waves compared to lower bands. But when you have concrete walls, yes, I mean, then it makes a bigger difference there. Yes?
From the user experience point of view, I really cannot complain about video quality, display, form factors, but the phone is still used for voice a lot. And is Samsung doing anything for the voice quality, like when I'm wearing a Bluetooth headset and dual?
Yeah, yeah. But the trend has been like until 3G, I mean, the still cellular networks were voice centric, but 4G LTE was, I mean, it started as a data only system, and then the idea was you can do, I mean, it's a IP based system, then you can do packet voice over LTE. Yeah, with the 5G, I think trend would still be the same. I mean, you will be doing voice communications basically on a data network. And I mean, with 5G, I mean, we also need to think about the new generations, right? I mean, people, I mean, so many of the young people these days, I mean, they are not using voice communication that much. I mean, they are more into SMS and other ways, I mean, through social network and other communications. But, I mean, the data capacities, I mean, for data, you need so much more capacity compared, I mean, the voice becomes just negligible in terms of the capacity that voice is going to take will be very, very small. So, I mean, you can use maybe the now wideband codecs to improve the quality or maybe other things as well. But, I mean, again, I mean, for 5G, I mean, voice is not the main focus point. It's still the, I mean, data. Yes, maybe. Yeah.
Would environmental factors be more important for millimeter waves, things like water vapor, rain, snow, related to performance?
Yeah. So I think when I gave a talk 3 years ago, we more focused on those issues. But the water vapor in our calculations, when you have a very heavy rainfall, it's like a monsoon. I think that only happens in maybe 0.0001% of the area of the planet, and not very frequently. But I mean, penetrating through foliage like trees. I mean, if your base station is on the other side of a forest, then of course, I mean, millimeter waves are attenuated much more compared to lower frequencies. But then our point is you can catch on to another base station or maybe a reflection and so on to cover those cases. Yeah?
So how was the efficiency of power amplifiers in the mobile side today versus what you might need when you actually have a form factor that's little with small batteries? So what would be the power efficiency?
So at millimeter waves, so we also are developing the ICs and for the millimeter waves. I mean, currently we can get up to 15-20% efficiency. We taped out some gas PAs. I mean, this efficiency is still low compared to cellular, where you can get up to 40% or 50%. I mean, that's my point. I mean, last point here is that I mean, a lot more research needs to be done in that area to enable these millimeter wave circuits for mobile communication. Yes, please.
An old saying, life is what happens while you're making plans. The real problem with DMC was a security vulnerability when you base it on digital anything. It's called cyber war. Based on something called boson site compensation, invented before. I told you about that. Right? So digits are an Achilles heel of digital crime. Simon Newton, 1881, invented the NLP.
Okay. I think earlier your comment was more about YouTube addiction. I mean, so I think yeah. Yes, I mean, of course, I mean, security is a completely, I mean, separate topic, and I mean, a lot of people are doing research in that area as well. But my point was with, I mean, YouTube, I mean, it's the way you use it. I mean, I'm using YouTube, I mean, just to listen to, I mean, these wonderful lectures that are available from the best schools and so on. I mean, that's more like a education tool for me, and this can be education tool for in the developing countries where there's no physical schools, and now people can have access to the best schools in the United States and so on. So, I mean, yeah, my point is it's the way how you use these applications. Yeah, thank you.
Thank you very much.
Yeah, thank you.